So I'm actually continuing now where that first video on integer programming ended. So we had graphed the, let me just redraw it so that you're able to see. We had graphed that new point, x1 is less than but equal to 3. We had discovered that it's definitely within this feasible region because point 3 is actually inside. The other intercept here is 3.33. That's why we can conclude that this point is definitely within our feasible region. So now, having known that, we recollect new values for x1 and x2, which we're going to feed into that branch which was like this. Let me just illustrate that new branch which had this x1 less than but equal to 3. Remember, there's also a branch this side waiting to be filled in, but we do one at a time, so that we don't get confused. So we now find like new values for this branch going this side, where x1 is less than but equal to 3. This is the line we've just drawn. So if you look at this line, x1 is equal to what? It's the 3, right? The same 3. What about x2? x2 is definitely this point corresponding to this axis, the y-axis here. That's why x2 will be found. So now how do we get the value for x2? This line is intercepting this line, So this line that it's intercepting had an equation of what? 6x1, if you remember from the beginning of the first video. And then it had 8 here, x2 less than but equal to 20, right? This is the line that this x1 less than but equal to 3 is intercepting. It's like now when you're solving for x2, right? Okay, you have that particular line there that has crossed, okay? And this x1 is equal to 3. You take it to that graph and you've seen why it's intercepting, right? The x1 is greater than 3, okay? So you want to find that value of x2 now, as according to this branch we are writing on our left hand side here. So you just have to substitute, of course, in this equation that the line intercepts. So what we'll just do is that, okay, we can just substitute the value of x1 in this particular. So I've put 3 there, which will be like 18, I believe. Then 8x2 is equal to 20, like you make it an equation. Then so for x2, what does it give you here? I'm getting 0.25 myself. Yeah, 0.25 as my x2 value, which I can now take in this box right there. Yeah, so that's how you locate your value for x2. On that particular branch for x1 is less than but equal to 3, right? So now you also want to test out this other branch where there is x1 is greater than but equal to 4. So as usual, first take it to the graph. That's when you will determine first whether you can pick points from it or whether it's feasible or not. Usually that's how we test these things in integer programming. So remember this original line, it's cutting the x-axis at it's cutting the x-axis at 3.33. please, let's remember that this is the point there. Now we're trying to plot x1 is greater than but equal to 4, meaning 4 comes just after that number, right? Somewhere there, x1 greater than but equal to 4. So that particular point, first of all, are we even going to pick points from there? No. Once a point falls outside your feasible region, then it's called an infeasible node. Is, as we said, infeasible. So remember, when a point that you're plotting on the graph is plotted outside the feasible region, that point is infeasible. And that's it, then you move on. Okay, so let us now see so far like how our branch and bound is coming up. So this was just like what I'm doing is that when I demonstrate something, I show you what's happening to the graph, and then I change back and show you like how your origin or branch and bound should be, forming itself as you are solving it in the exam. So you would have, okay, those are the origin. So having seen that, okay, we will not end here. As I said, we only stop a branch and bound problem when all integers disappear. So meaning you continue branching off as long as you're not seeing as long as you do not have whole numbers, then you continue branching. So there will be a branch, there will be a branch. Which one do you branch off? Remember, what you branch off are the x1 and x2. Do not mind z. What you branch off is x1 and x2. Those are the variables you're trying to maximize in this particular function. So x, again, you're branching off x2 in this case. It's the non-integer number in that branch. So you always branch off a non-integer. So what are the two bounds of 0.25? Well, the lower bound is 0, right? Yeah, and it should be an integer. And then what about the upper bound of x2 in that figure, 0.25? Well, that is 1. Okay, that's the closest number into the upper bound of that figure. Then go to the graph again. Always when you branch off, go to the graph so that you can plot those points and see if they are within your feasible region. So let's replot this. You always take note of all these things. And now you need to plot those new x2 bounds. The first x2 bound is x2 is less than but equal to 0. What point do you think that is? This is the x2 part of the graph. This is the x1 part of the graph. They tell you x2 is what? Less than but equal to 0. Meaning you just be going along this line. This x1 line. That's x2 is the less than but equal to 0. That is the line you're looking for. So if you follow that line, you know that your x2 value, we said it's what? 0 less than but equal to 0, so it's equal to 0 when you're now picking the new points. What about your new x1 point according to that branch? If you look at x2 is equal to 0, it's just going along this line. So the moment it touches this one, this line which has gone vertically up, this one which is x1 is equal to greater than or equal to 3, this same point, that's why you should stop. One might wonder why aren't we reaching the far end to where the original graph was cutting. Reason is that this line we've just put here, right, the x1 is greater than or equal to 3, is now part and parcel of our graph. So the first line that any intercept catches, that's the one we consider. That's just how it is. So like we're following this line, x2 is equal to 0, meaning you're just moving along the x1 line until it touches any line which is on that axis. And in this case, the line we have touched is this one, which I'm circling. x1 is less than but equal to 3, meaning your new x1 point is what? It's 3. If your x2 is 0, what is your x1? It's 3, because that's the only line, that's the first line that it's cutting. Yeah, that's why we found 3 there. So if you, even when you go back to your branch now, we get back to our branch. Remember we had a branch like this with a bound of that, with a bound of 0. There was this branch here and a new box. So your x1 now we said is 3. Your x2 is 0 as per branch, because the branch determines the value even already. And you can even now compute your new z as of this box. It's 9. Remember the objective? This is the objective function. We always test when we get new values. When you fuse in those values, you should get 9 for z. Then remember there's another branch coming this side. This was the one which had that x2 greater than but equal to 1. If you go to your graph, this point, I'm just putting the graph this time around, I'll put it below. Of course it's the original graph. I'll just show that it's the same original graph with the same intercepts. You have that line that greater than but less than but equal to 3. That was that line, less than but equal to 3. Then now they're asking you to plot x2 is greater than but equal to 1. How would you plot that one? This one would come like this. I think point 1 can be there. Then when you draw, x2 is less than but equal to 1. Like that. That's how that line will look. This is the x2 is greater than but equal to 1. So what points do you have at this point? What are your new points as per this branch which was x2 greater than but equal to 1? You find that when you check through this, it's cutting which line? This one, which is again, this line, the x3 line, right? It's cutting the line again. If you follow this, x2 is greater than or equal to 1, it's cutting this line first. So meaning the x1 point is at that same one where they are cutting, the 3. How about x2? x2 is given by the branch in question, which is this branch, which is x2 greater than or equal to 1. You put the 1 there. The new z value as of this branch should be, if I'm not mistaken, just a minute. I think this wasn't just drawn accurately. It's supposed to come out like this. Sorry. It was supposed to be like that, something like this. Yeah. If I remember, it's just it wasn't drawn to scale. The first line that this x2 is catching is this slanting line, and we know that this slanting line has this equation: 6x1 plus 8x2 greater than but equal to less than but equal to 20, right? And the rule is that to find the values, like we already know x2 is 1. Now we want to find x1. How would you find x1? You find x1 by substituting it in the equation of that line that it cuts, so it intercepts with first. This time it has intercepted first with this one. So you substitute an x2 value in there, you should land with an x1 value of so much. Let me just put this down, what I meant. So like this is the equation that that line cuts. So when you like substitute as per branch, which branch are we dealing with? The x2 is greater than or equal to 1, meaning your x2 is 1. You substitute there. Then your 6, you're looking for x1 as of that bound. When you do you change the substitute of the formula, you should land with an x1 value of 2. That's what was supposed to go here. So we'll just make that correction. So of 2. And you're done, just like this, you're done. Then you now begin to reason on this. Let's just see, this one will give you a z of 8 actually now. So look at now your bounds. You've reached here, you've been bringing your branch and bounds from the top to this point now. Do you have integers as of now? The answer is actually yes, you have integers. So now, which one do you go for? Because both branches are appearing like they both have integers and you can go for any of them. So which one we go for is just determined by what condition is the question asking you of. Is it a mean question, minimization question, or a maximization question? If it's a maximization question, go for the highest one. We want producing the highest z value because we are maximizing. Therefore, we would pick this and just write that the optimal solution is equal to z is equal to 9, x1 is equal to 3, and then x2 is equal to 0. That's the one we pick. And that's it on integer programming.